Hello everyone, I'm Alex Jacobini and I'd like to present about our 3D scanning project at the corpus of my hieroglyphic inscriptions at the Peabody Museum, what kinds of things we've done so far, and how the museum could benefit, various projects the museum could benefit from our data, what uses we've had so far, and how we expect to share it in the future with various scholars and the general public alike. So this presentation will touch upon several key issues. The first one is how and where do we collect 3D data? When we talk about 3D scans, it's actually a diverse variety of techniques and a diverse variety of types of things we extract from the objects around us that we all call 3D scans. We'll also talk about transforming the original data that we generate using various techniques and tools into the final 3D models, a typical workflow using some of our common types of software in the project, available to the project. We'll talk about some of the decisions that we need to make while we're working on 3D data, things like resolution and compression, uses of 3D models, for example, printing or milling, creating physical replicas from digital data, but also research uses, specifically studying ancient monuments, ancient inscriptions in epigraphy or iconography, virtual reconstruction, and then educational uses. We'll also discuss types of files and the questions like data migration, which may eventually affect our 3D archives. And finally, our current way of sharing things with a large number of general public users or research users through the Peabody Museum 3D Gallery and also its Sketchfab account, which in turn powers our public 3D gallery. So the first question is how we collect 3D data. It's very important that when we talk about 3D, generally speaking, most of the time we're not discussing CT scans or microwave scans or X-ray scans. Instead, we're discussing different techniques of measuring the topography of the surface using some kind of optical device. So we're taking measurements. That's very important. That's the difference between, say, a 2D scan and a 3D scan. And we can take measurements of the surface in a number of ways using photographs, using lasers, using motion Kinect types devices, but also using the so-called structured light scanners. So photogrammetry is the most straightforward way of capturing 3D, and it has been becoming a kind of mainstream technology in archaeological documentation. So in the same way as today, our museum stores photographs and drawings from several archaeological projects. It is to be expected that within a decade, the most common way of archaeological documentation would be 3D models derived from photogrammetry. It's just so easy to do. The most common technique is the so-called structure in motion. So an observer positions a camera at different angles, but also slightly different viewpoints in relation to the documented objects. And then a specialized software derives measurements, so a cloud of points that corresponds to the topography of the object based on differences in angle and positioning of the camera that captured the photograph. So here you see a few examples, say an average scale ancient Maya monument that I just captured this April at the site of Naranjo in Guatemala, or a relatively large stucco facade of a temple terrace in the upper right corner, or a relatively small Egyptian artifact. So we can apply this technique and it's scalable and we can get different resolutions. It's easy to do. The software is pretty straightforward. The cost is remarkably low compared to 3D scanners, even though you do need a good camera. Now you can mount the camera on a drone. Once again, they have come a long way from these relatively bulky devices like a helicopter you see here I photographed in 2009. Now they're much more accessible and they're easier to operate. And so that becomes the mainstream mapping technique for archaeological projects. So capturing very accurate maps using structure and motion photogrammetry, using light cameras, high resolution cameras mounted on drones. Now, laser scanners are another kind of mainstream technique of documenting objects in 3D, creating point clouds of measurements of the surface topography. And they're relatively small and portable laser scanners. Our next engine is the most common variety of a small portable scanner. We have one in the Semitic Museum that Peter Manuel and I acquired for one of the courses on digital illustration and photogrammetry that we actually taught here at Harvard. Then there are larger scanners like Leica laser scanner, which can be used to scan entire structures. You see here the Leica scanner is mounted on scaffolding and captures an entire section of the temple of the hieroglyphic stairway at Copan. Or the same scanner can be used to document relatively small objects, but the resolution is still relatively low compared to smaller laser scanners or to the so-called structured light scanners. So structured light scanners project moving patterns of shadows onto the surface of the object. They have to be relatively close to the surface because those shadows have to be crisp enough. The contrast has to be high enough for the software that reads the data from the cameras to recognize the surface topography, to calculate the surface topography based on the distortions to those moving patterns, changes in the shade of gray, phase shift, produced by the surface topography. These scanners, the structured light scanners, are the most precise, the most accurate optical 3D documentation system. They're also the most expensive. Most of our 3D data was generated using one of those structured light scanning systems built by the German company Brookman Icon. Our smart scan is also a modular system, so by changing the lenses, we can extend the area that the scanner captures with a single shot, or we can reduce the area. So if the area becomes reduced, the resolution, the distance between the points becomes smaller and smaller and smaller, so we get high resolution, high density of points, but a smaller scan with a smaller depth of view. So we can basically decide whether we want to spend a lot of time scanning the same object and obtain an incredibly high density point cloud, or we want to spend less time and obtain a point cloud of lesser density, for example, when we want to scan a larger object, when we're not sure even if we would be able to process all that data that we capture with the scanner. We worked in all kinds of contexts in which you can document monuments and artifacts, and museum collections, for example. Here at the Peabody Museum or at the Barton Oaks in Washington, D.C., we also worked with the collections of the Louvre Museum, collections in Guatemala. So here we are in the Morley Museum at the site of Tikal, or at the Archaeological Park of Quirigua, regional office of the Institute of Archaeology of Guatemala in the town of Melchor de Mencos, or the regional research office at the site of Copan in Honduras. We worked in the field. We took our scanner to the jungles. Here you see us on our way to the Holmul Field Camp, where we documented 2 incredibly fragile stucco friezes. There will actually be a story in National Geographic coming out this September, and its online version is going to include a 3D model of the frieze that we did for the Holmul project. One of our largest endeavors in terms of 3D documentation with the structured light scanner was creating an exact replica of the Copan hieroglyphic stairway, which will in turn enable us to create a new digital reconstruction. Basically, more than 2/3 of the stairway are currently restored in an incorrect order. So all the blocks are pretty much in a random order. So we wanted to create an accurate reconstruction of the stairway. Not using the real stones, real blocks, but their scaled 3D prints. So this project, the project of documenting the stairway, took us 4 years, and we had to come up with all kinds of little clever solutions to be able to access these incredibly large monuments, the largest surviving pre-Columbian inscription, one of the largest inscriptions in the world, as a matter of fact. So every step of the stairway is covered with inscriptions, with inscribed characters. And we also worked in places like archaeological tunnels, so documenting fragile stucco facades preserved within later buildings. So here we are at Holmul, but we also worked a lot at the site of Copan, documenting early classic building facades. So what kind of data does a scanner generate? Scanner generates measurements. So these are point clouds. So for example, our structured light scanner can capture say 800 point clouds, each 1 million points, which correspond to a surface of an object. Each point cloud has coordinates which related to the other point clouds of the scanning project. And then, for example, a structured light scanner will also capture color values for each point, and then separate color images with coordinates. There may be additional metadata that comes with the scanning software, for example, the temperature of the sensor, the calibration of the sensor. And then there are various programs which will analyze the data. Say photogrammetry programs will allow you to extract 3D data from the photos that you took following a certain set of procedures. And then most scanners come with their own software. Say our structured light scanner comes with the software called OptiCAD. Next Engine comes with its own scanning software. Most of the Kinect devices, like a portable Sense scanner, will come with their own scanning software. And then there are certain programs which are universal. So Polywords, Geomagic offer packaged solutions. Generally, we do not use them. We find them a bit less efficient than the scanner-specific software options, but we do use Geomagic for processing of finished 3D models. So what is a typical workflow like? So first I get a point cloud from my scan. I may have to mask it. So I may decide which points are actually good points and which points I want to avoid. So each scan is 1 million points, but I may actually be using no more than, say, a couple of hundred of thousands of points, and no more than that. So maybe 20% of the full point cloud. I may apply a certain filter and a certain sampling. So I may tell, for example, use only 10% of the points. Then I generate a mesh. So I replace points with triangles. So I create a surface out of a point cloud. Then I may apply additional filters and compression. So for example, I may try to increase the size of triangles if the neighboring triangles are not substantially different by angle. Or I may try to remove triangles which seem to stick out of the surface, or when the angle change between any two triangles of the mesh is too steep, too substantial. I have to align my meshes with each other. So say if I have 800 point clouds, I also need to align all the point clouds and all the meshes together. And then I merge them into a single surface, thus, first of all, removing all the redundant data, and then potentially choosing between different overlapping meshes, choosing the good points, the good triangles, the more reliable ones. For example, calculated based on an angle between the scanner and the surface that it captured. I may apply additional filters, fill the gaps, and then I get my final mesh, which I tend to save as a PLY file, as we're going to see. I'll talk a little bit more about the different file types. At this point, I have my archival copy. I may need to make changes if I want a 3D print of it. For example, I scanned two surfaces of a hieroglyphic step, and I cannot scan the other two sides because they're embedded in the fill of a structure. So unless I take that rock out, I can only capture the visible parts of the step. But for a 3D print, I need to create volume. So I cannot just print two sides. So I may use different techniques, creating thickness to my scan. So creating a back, the other missing sides of the block. Those, of course, would not be relevant for archival purposes because they're fake. They're just my modern creations. But I need to do something when I create a 3D print. But I also may make specific changes. For example, some form of connection that would allow me to articulate this block with another block. So there's a little bit of engineering, but also specific input based on how you expect your model, for example, to be incorporated into a museum exhibit. Say if it's mounted on a wall, I want my 3D print to include, say, some holes for mounts, and I can do that. So here's an example of the so-called project folder that our scanning software generates. So where I'm scanning, in this case, a set of blocks of the hieroglyphic stairway of Copan, and once I click on the folder, that's what I see. So that's different types of data that the scanner generates as it goes. First, there are the point clouds, so the actual measurements taken by the scanner. There are preliminary meshes that the scanner generates before it creates a single merged mesh, and those can be generated and generated again from the point clouds. I can generate an endless variety of meshes. Depends on what kind of parameters of masking, of data reduction I eventually chose. So it is very important that even though the scanning itself is a very advanced, very accurate, very precise technology, the processing entails a lot of personal choices. So no 3D model is alike, and that's why when we say there's a 3D model by the Peabody Museum, we indicate the author, say myself, by Alex Duchovny, because I, as an author, introduced a lot of personal choices into the production process. So certain filters, but a lot of manual editing of the final mesh as well. Then the project folder includes the camera pics, the coordinates for every mesh, for every point cloud, sensor data, so referring to the type of calibration. There's a folder for merged meshes and additional metadata, once again detailing the types of capture settings for every mesh. So for example, I could tell the scanner to use a single capture of the surface, or to take the same measurements 8 times and then use the average values, or to take them with 2 exposure settings and then combine the best data. So there are all kinds of possible settings, so all kinds of choices involved in the capturing process. And of course, the more advanced is your scanner, the more advanced is your software, the more choices you potentially have, so you can impact that, which can impact the quality, the nature of the resultant data. So here we're just looking into the AutoCAD software. You can see there are all these different options. Here we're looking at just 4 scans. They're listed on the right out of 45 point clouds. So we had 45 million point clouds, and we end up with approximately 20, 30 million triangles in the final model. And once we merge those individual meshes generated from individual point clouds, then we end up with a final model. And so these are just some of the options that we use in our 3D scanning routine. So for example, we introduce certain types of labels into the names of our files. So just in case, imagine that all the metadata is lost, there is still some indication of how that particular model was created. So sampling. F means no sampling was introduced into the point cloud. So it's just based on the real point cloud. So F full means archival quality. S means standard or some subsampling. P means preview. So heavy subsampling of the point cloud when the mesh was being generated. We can also introduce additional decimation. So reduce the quantity of points used for creating the mesh even further. And then once the mesh is created, we can apply compression. So optimize the topography of the mesh based on how much surface variation we want in the final model. So we can make it basically smoother with fewer triangles, so a smaller file, but potentially losing data as a result. So high H means highly compressed mesh, S means average compression, low means low compression, R means raw data. No numerical values here, unfortunately, in part because there's a lot of variation in how we take specific, how we process specific data sets. So rather than introducing numbers, we prefer to have these broader general categories under which we operate. So if something is F, full, 1, no decimation, R, that's as close to the raw data as you can possibly get. But then it is still a merged mesh. So it combined all the individual point clouds and meshes generated from them, and then went through some kind of selecting process, merging them into a single surface. So here's an example of 3 different resolutions. So generated from the same data set, from the same point cloud. Right, there's this raw data, 700 megabytes, and a highly compressed data of just 120 megabytes. Obviously, you need computers with different kinds of computing power, a different quantity of RAM. So the smallest model, you can actually view it on a portable device, on a cell phone. You need a relatively powerful personal computer, workstation on a Mac to view the larger model. But then it's all about why the goal of your archival operation and possible uses. Say you just want to show it to the students in class or to somebody from general public, you're probably fine with a low resolution model. If you want to have a record of the surface topography to measure erosion over, say, a period of time, or if you want to create a copy that then may be used to create actual physical replicas, then you probably need the highest resolution possible. So in terms of reproduction, there are two basic techniques. One of them is milling. So there's a machine, the milling machine. It's a PC, computer-controlled drill that moves either in 3 directions or in 5 directions. The 5-directional ones are obviously more expensive, and cuts a material. And there are different types of material. It can be stone, can be metal. Quite often they use high-density industrial wax that can later be used for a more conventional cast in a sturdier material. So essentially it's a 2-step process. And creates a replica by essentially cutting that chunk, that bulk of whatever material of your choice into the image of the object layer by layer. So it's a reductive process. Here's an example of a stucco facade from the structure at a called Margarita. And you see that the company in charge cut it in 3 sections. And of course, their models were modified. So in addition to our scanning data, they created sections. They modified the backs of the models in a way that they could be articulated with each other, could hold together. And they were, in this case, carved out of high-density foam. So they were substantially lighter than the original object had been, so they could be moved around. And they had to be painted by hand, unfortunately, because most of the milling machines cannot incorporate the painting, like automatic painting process, into the main production workflow, though. So painting has to be done by hand at some point later in time. Now, additive printing is done a bit differently. In this case, the material is added in layers, and it can be a plastic, starch, kind of it can be metal, burned by laser beams. It can be material that solidifies when it is exposed to UV light, like dental filling. This is a relatively common and inexpensive printer maker bot that uses a kind of hot plastic that basically cools down and solidifies as it comes out of a nozzle of the printer. So in this case, the material is added in layers. So not removed in layers, but added in layers from the top of the printer. Here's an example of a really high quality print using some kind of starch rather than plastic. And they had to print it in sizes, in chunks of certain size, so smaller sections. You can actually see the, the gaps between the sections here. But the resolution is quite impressive, generally a bit higher than the milling machines can offer. So here's our primary project of creating small scaled models of the steps of the hieroglyphic stairway to be able to create a new reconstruction. Here's our team: Dave Stewart, myself, Bill Fash, and Barbara Fash, standing in front of the full model of the stairway in its current state. If you go to the MATLAB now, you'll actually see different reconstructed sections. So the blocks not in their actual order, but in the order, in an order that we actually think they were when the stairway was in use. I'm a epigrapher myself, and epigraphic line drawing, so a kind of communication tool is an essential part of my field. So I create these line drawings to communicate my interpretation of the eroded surface of the monument, highlighting lines which I believe reflect the actual carving, as opposed to erosion, intentional breakage, or any kind of features that your eye may see, but my trained eye may suggest are not perhaps as important. So line drawings in epigraphy are a key tool of communication between epigraphers, and also between epigraphers and non-epigraphers. So we trust each other in reducing the amount we need to stare at a surface of an object using different directions of light by creating these maps, and that's what they are effectively, of the image and the text on monuments. And of course, we use certain types of conventions to do so. 3D scanning is an incredibly powerful tool because it allows us to visualize objects without distortion and in ways conventional photography cannot. So here's an example, a photograph of steel 17 from Tikala 3D scan, no distortion, and then little details literally come to life, and you can modify drawings. So you see a passage here, and in red there are different details which are only visible in 3D scans and much harder to trace using conventional photos, and they are important. In the case of this monument, we can actually identify a familial relationship between the rulers of two important sites during the so-called early classic period. The king of Tikal turns out to be a maternal grandson of a king from Shultun, both sides documented by Harvard scholars at various times. But it's a key moment in the classic Maya political history, and to be able to confirm an important relationship between the two kingdoms at a crucial moment in the political history of the region is very important, and this 3D scan enabled us to do it. It will be probably unfair to say that 3D scans are the only kind of data that we use. So right now we're in the process of drawing Yashchilan monuments. And if we can, we use 3D scans, we use photographs from the 19th century, we use modern photographs, we use photographs by Ian Graham done in the 70s. We combine all these kinds of data, sometimes in huge files where all the images are modified and layered one over another. So we produce accurate drawings which cannot be derived from any single type of data. Instead, it's a combined data. It's our analysis of all available data sets to produce this composite image that reflects our understanding of what was actually there on the object. Now, but also at a time when the first documentation took place. So sometimes we create multiple screenshots of our 3D scans under different conditions, of imitated conditions of light, then combine them and then use them for drawing purposes. We can also add details which are not necessarily on the object, but which exists separately. So here's a section of the stucco facade from the site of Homul, which at the time of its documentation was not there. It fell off during archaeological excavations. And with the help of a stucco conservation specialist from Mexico, I was able to reconstruct part of this damaged and fragmented section. So I wasn't obviously the person doing the actual putting of the stucco fragments together, but I could help because I could understand the glyphs and therefore assist in how the different stucco parts actually articulate with each other. And then the stucco conservation specialist would glue them all and check the connections. It takes a lot of patience and training to do so because the stucco is a very fragile material. And then we were actually able to scan that section and add it to the Frieze 3D scan digitally, so without necessarily endangering the fragile damaged stucco sections. And we were able to obtain a new spelling of a key place name in the 4th and 5th century AD hieroglyphic inscriptions in the Maya land. So sometimes a single glyph in stucco can be incredibly important for archaeological research, and 3D scanning offers new ways of adding and extracting new data and combining with different types of our available sources. Another great example of working with fragile things using 3D scans is our work on the so-called eccentric flints from a single cache at the site of Copan in Honduras. Those stone artifacts in themselves are not fragile. I mean, not as fragile as to prevent any type of conventional analysis, but they're wrapped in textile. And so those fragments of textile, which still remain, effectively prevented lithics specialists from drawing and measuring sections of these artifacts. So we resolved this problem by creating 3D models, which could be rotated and viewed under different angles without necessarily endangering those incredibly fragile pieces of textile, which are still on those objects. There are also intangible properties which may be revealed using 3D scans. So I worked with a scholar who wanted to study shadows cast by Roman oil lamps. So today, most museums would not allow you to put an oil into an ancient Roman lamp, light a fire, and see where the shadows go. Or perhaps put an electric light or manipulate a lamp in a way that would, create those shadows. But with 3D models, it's relatively easy to place a scanned object, a digital replica of an object, and then recreate shadow patterns. And so see a play of images, which perhaps was intended when this lamp was lit. It had multiple sources of light casting different shadows, under different angles and producing different images, perhaps with different kinds of visual puns. So once again, 3D scanning enables us to do this type of work, which is no longer possible in this case because we simply do not want to endanger objects, ancient artifacts, museum collections that we work with. So different uses obviously entail different types of digital files. So for our archival quality models, we rely on Stanford Polygon 3D meshes. We choose this file because it is one of the most common formats today. So even though there is no standard, or say the current standard established by the Library of Congress for 3D files is essentially 20 years behind the technology and cannot be effectively used for storing large 3D meshes, Stanford Polygon is one of the most widespread standards, and it's the only standard that allows you to combine 3D measurement data and color data into the same file. So with Stanford Polygon, the triangles, the mesh triangles, the points themselves retain color information as well, not just the topography of the model. The most common format used in printing, on the other hand, is STL, stereolithography, also called standard tessellation language, but that's a retrospective acronym. It's not the actual name. And this technology is used by most 3D printers, obviously those which do not print in color. And then a lot of online data, or the data meant to be shared online, is in the OBJ, on the wavefront format. Now, files tend to be larger in the way they represent topography. So if you want to represent a certain amount of topography, PLY is the most efficient way. But OBJ allows you to separate the color of the object into a separate file with coordinates related to the topography of the object. So you can create objects of relatively simple topography, so perhaps not very accurate representations of whatever you documented, and incredibly high resolution color images attached to them. So it may look as if the object contains all the detail. It actually does not. So for digital, for online sharing, this is a preferred way of doing it, because in this way it minimizes the amount of time it takes to load your 3D model and the amount of processing power, the computing power your device needs to view a 3D model. So we have some of these objects in OBJ format because we expected to share them through our Sketchfab powered museum 3D gallery. We have some STL files whenever we actually expected to print something at a certain size, a certain resolution. So those are sort of special purpose files. And then we have lots of Stanford Polygon files. And usually we have an archival quality copy, but we may also have 2 or 3 or more additional files of progressively higher compression and lower resolution, because some of our files are so large that we understand perfectly well that we wouldn't be able to share them yet, at least with most scholars. So we create those reduced copies to be shared in case people simply cannot open our files because they're too large and their computers don't have powerful CPUs, powerful video cards, or enough RAM to view our files. So we're aware of those sensibilities and we try to meet them by creating additional copies in lower resolution, higher compression of our 3D data. So as I already mentioned, when you print something, you create volume, you remove potential errors, you simplify, you scale the model. There's some companies will take care of those costs, but then they would be added up to the cost of printing if you outsource it. If you're printing yourself, you obviously have to do it. We have software which is relatively good for those tasks. It's an expensive software. It's called Geomagic, but it can effectively prep your models for printing. Then all you need to do is just send them away to a printing company. So here's an example of our one of our recent projects, in printing project. So we scanned this incredible monument, the Chinese tercentenary Harvard tercentenary stele, several years ago, and here's a file in Geomagic that is prepared for printing. So not only it is completely sealed, it is a shell. So we created thickness. So our stela here at a scale, so it's only about 20 inches tall, not the real size. It is not a solid piece of plastic. That would be very expensive if you were to print it with an additive printing process. So instead, it's an empty shell that is only about 5 millimeters thick. So it is thick enough to retain its structural integrity when it is printed in high density foam or plastic, but it is still empty, so it's relatively light and less expensive than a solid model. So you can use different types of software to generate this effect, but obviously it is a kind of post-scanning modification. Those added features are not part of the original object. So you may not want to store this as your archival quality copy, but it is a useful file to have in case the museum gets a request from somebody who wants to have a scaled model and a print of a stela. Now, our Sketchfab account is our primary way of sharing material with the general public and with other scholars. So in case people do not have the means to view files in specialized software. So we post models to our Sketchfab account, and our models are private, with one exception of the home will freeze. They are not accessible through Sketchfab. So people who view our Sketchfab account online, they will not see anything. The account is registered to Steve Rothman, and I'm the only other person who has access to the account. Now, our 3D gallery is obviously managed by a website technician, and then Pamela Girardi is the person in charge of the decision-making process. So I have a 3D model, and I think it would be a great model to put online as part of our Peabody Museum Collections 3D gallery. And so I write to Pamela, she views the model in a private mode. She thinks it's okay, it's a great idea, and then our website technician takes care of adding it to our museum gallery. So we have a 3D gallery as well. So first we upload a model on our Sketchfab account, and we own these models. They don't belong to Sketchfab. Sketchfab is just a hosting site. They just provide us with a service. We list this model as private, as you can see here, and we do not allow downloading the model. So say if we want to work with a scholar and they want a copy, we can briefly enable a download while we provide the person with a link. So the person can view it online, or the person can download a copy if we so wish, and then we can cancel this option once again, and the model is no longer downloadable. So all of our models right now are not available for download. And then we can copy a direct link. So sharing it with a specific scholar. So the model can only be accessed through Sketchfab by somebody with a link. Or we copy a viewer code. And that's how our museum web gallery works. So we have the so-called iframes, a code embedded into our website. And just like YouTube video, the model itself is hosted on Sketchfab. That provides all the functionality, or visualization functionality for the model. What the visitor to our website sees is an iframe, just like the YouTube video frame, that links a view of the model to Sketchfab. The Sketchfab powers the visualization process. And then this way we get beautiful image, but it is still linked to our PBD account. It is not available directly through Sketchfab. So this is our 3D gallery. So every time I click on one of those iframes in our 3D gallery, it is actually powered by Sketchfab. So it opens in 3D model, I can move it around, I can zoom it in, but all the settings are manipulated. All the visualization settings are controlled by Sketchfab, by our Sketchfab account, and we can modify them at any point in time. We can annotate the models. So we have a couple of annotated models in our PBD Museum gallery. So in this case, people can actually read individual glyphs on a hieroglyphic plate from the side of Homul in Guatemala. So the advantage of these new technologies is not about cool visuals. We can also add different types of metadata, links, annotations, commentaries, establishing a dialogue between us, the museum, and our potential visitors, who would then be perhaps compelled to view our objects in real life. So as I already mentioned, all of our objects except the Homul stucco frieze, and that was a specific agreement with the project, with the Homul project, are in a private mode. Researchers may access the objects through special links. The resolution is not so great compared to the resolution of our archival models, but it pretty much matches an average computing power of a PC or a Mac. Most of our models are too heavy for portable devices, but we do have some which have been simplified enough, and of course there's always an option creating a separate gallery or a separate secondary version of our models specifically for portable devices. So it's probably the most efficient way of sharing data with potential users, apart from really high-end researchers who have access to powerful graphic workstations, or perhaps in the near future when everybody has a personal device which is as powerful as today's workstation, which, of course, as we know, will happen eventually, just a matter of how soon. Finally, the last point that I wanted to make is the fact that our models are already enabled. So our PBD Museum 3D Gallery is technically enabled for virtual reality devices. So if somebody with a powerful virtual reality tool like HoloLens or any other kind of PC or Mac connected virtual reality device can view our models, but also viewers with personal devices like iPhone can actually click on an icon in a representation of our 3D model. So if they log in, they open a 3D model, there's a little icon they can click. And then instead of a single image of a 3D object, they will see two images. And then with a cheap device like Google Cardboard, costs like $10, or you can make it yourself. Here's an image of one of those Google Cardboards. You insert your smartphone into a Google Cardboard, and you can actually view a really three-dimensional image of an object, a stereoscopic image of an object that you can manipulate by turning your head around or actually moving around the object in the same way as you would walk around an object in a museum gallery. And then turning your head, you just basically look around and you see everything in 3D. So once again, we already have all of these functionalities embedded into our 3D gallery. The only snag here is that many portable devices are not powerful enough yet to be able to visualize the objects at the maximum resolution available through Sketchfab. So we have to downsample them if we estimate that our primary user is going to view the models through a portable device, or that our primary user is going to use something like Google Cardboard, because when you visualize a double image, it means that you need the double processing power for the object of the same resolution, for a mesh of the same resolution. But the most exciting news, I believe, is that this technology is already there, it's available, and some of our users can enjoy not just digital 3D models, but stereoscopic, like real 3D objects through our museum website. It is already there. These functionalities are already embedded, and we can just expand and build upon these functionalities if we so wish in the future.